Hello there, welcome to another lesson on vectors. Today we will be taking a look at column vectors. We will be talking about the sum column vectors, that is finding the resultants of column vectors. We will also be taking a look at how to find the magnitude of a vector. A vector is a quantity that has both magnitude and direction. We have already talked about that in our earlier videos and earlier lessons. So we can represent a vector in this form, that is a directed line segment, a line that has an arrow to show the direction of the vector. In this form, we have shown that the vector has a start point and it has an end point. We sometimes refer to the start point as the tail and then the end point as the head, or we call the start point the initial point and the end, we call it the terminal point. So we have here different vectors represented on the grid or on the Cartesian plane. Now the vectors we have represented here can all be represented as column vectors. They can all be written as column vectors. Now let us take these as examples. We have the vector AB. We have the vector AB, which shows a line segment with initial point A and terminal point B. Now the movement in the X direction and the movement in the Y direction make up what we eventually write as the column vector. The movement in the X direction and in the Y direction that eventually describes the line or the directed line segment is what we refer to as a column vector, or what we write as a column vector. So representation of the column vector is what we have here at the bottom. We have for AB, we have for CD, we have for EF, and we have for GH. Now this representation shows a number on top and a number at the bottom, a number on top and a number at the bottom. The number on top is the movement in the X direction, which could be to the right or to the left. Then the one at the bottom, that is the number at the bottom, is describing the movement in the Y direction, which could be to the top or to the bottom, which can be described as up and down movement. So for example, I will start with the vector CD. The vector CD has a start point at C. So how many steps do we have to move in the X direction? Of course, my direction will be in this way. That will be movement to my right. So I'm going to have 1, 2, 3, 4, 5. I have moved 5 steps to my right. Then 1, 2, 3. 3 up. So we have 5 to the right and 3 up. 5 to the right is going to be plus 5, and then 3 up will be plus 3. So the column vector for CD is 5, 3. The same we have for EF. Now EF, the start point is E. How do I know the start point? Because the arrow is showing me that it is a movement from E to F. The vector EF shows the movement from E to F. How do I know that? I know that because the arrow showed me that it is from E then to F. That is why I have called it EF. So I'm going to move from E to F. Now my start point is this. Now the movement will go in my right. So I have 1, 2, 3, 4, 5, 6 to the right. 6 to the right means plus 6. And then 1, 2, 3, 4. 4 down. So the Y is going to be minus 4. Why is it minus? Because the movement was downward. Movement downward will be negative for Y. The movement to the left will be negative for X. I'll come again. Movement downward will be negative for Y. and movement to the left will be negative for x. In the same way, we can describe the vector AB as a column vector. So let's start from A and move towards B. Horizontally, I have movement to my right because the arrow shows to my right. So I have 1, 2, 3, 4. That's movement to the right 4 times. Now there is neither a movement upward nor downward. So there is no change in the direction for up and down for this particular vector. So that means the movement up or down is 0. So I have 4 for x and then 0 for y. So we have been able to represent all the directed line segments here as column vectors. In the same way we have all represented as column vector, we can also have the reverse vectors of each of them. The reverse vectors represent what we have earlier talked about in our earlier videos and lessons as negative vectors. Negative vectors or reverse vectors refers to the vector that is in opposite direction to an initial or a particular vector that was described. For example, we have the vector AB, then the vector that is the reverse vector of AB will be BA. And BA also means the same thing as minus AB, or the negative of AB. In that case, BA describes the movement from B to A as against the movement from A to B. The movement from A to B is the vector AB, while the movement from B to A is the reverse vector BA, or we can write that as minus AB. If we have a minus for the vector AB, then the minus multiplies both the x and the y component. The x component becomes minus 4 and the y remains 0. For the vector CD, the reverse vector is DC, and then if we have the reverse vector, that will be minus CD. Minus CD means a minus will multiply the vector CD to give us minus 5 for the x component and minus 3 for the y component. The same will go for the vector FE as the reverse for EF and the vector HG as the reverse for GH. Now, this time around, we have decided to label the vectors that we have initially described with the start point and end point. We have decided to represent them with small letters or lowercase letters. So vectors can be presented as a directed line segment showing their start point and their end point with capital letters, or they can be represented with just a lowercase letter that can be used to describe the particular vector. The vectors that we have initially described, we have decided to represent them using the small letter and also the capital letters. Remember, the capital letters, which shows the start point and the end point, or which shows the initial and the terminal point, can also be presented in the same way, but this time around with small lowercase letters. So as you can see right here, we have the vector M, that is minus 1, 3, the vector N, 11 minus 1, we have the vector P, 2, 4, and then we have the vector Q, we have 3 minus 1. In the same way we have talked about the reverse of the vectors when we wrote them as 2 letters showing the start point and the end point. In the same way, we can also talk about the reverse vector of the same when we have represented them as a small or lowercase letters. So we have the negative of M as minus M, we have the negative of N as minus N, and then we have the negative of P as minus P, and in that manner we go. So if we have M as minus 1, 3, then the reverse will be minus M. That will be 1 minus 3. How? The minus goes in to multiply the minus 1 and then 3. So we have 1 minus 3. The same we can do for the others, and then we get the reverse vectors. So here are practice questions that you can take a look at on your own. Now let us talk about the magnitude of a vector. The magnitude of a vector simply is the length of the vector. We have represented the vectors earlier with a directed line segment. You would have noticed that the line segments are of various lengths. We can decide to talk about that as the magnitude of the vectors. Now, the magnitude of the vector can be found using the Pythagoras rule, but we will not want to uh, bother us with that. We will just go ahead and talk about the formula that can be used straight away to find the magnitude of a vector. Now consider the vector P, which is 2, 4, and the vector M, given here in the diagram, minus 1, 3. The magnitude of any vector of this kind can be calculated as the square root of x squared plus y squared, where x is the x component and y represents the y component. Remember, we have said that the number at the top is the x component, the bottom number is the y component. So the vector's magnitude can be found by using the formula square root of x squared plus y squared. Now this can be written, for example, the magnitude of vector P can be written as in this form that we have here with a 2 slash by the side of a P, then that will be equals square root of x squared plus y squared. So the magnitude of P, if we solve that, that will give us 2 squared plus 4 squared. Of course, that will give us 4 plus 16, and that is root 20. And if that is simplified, that will be 4 times 5. And finally, 2 root 5 as our answer. In the same way, we can find the magnitude of a vector M. Magnitude of a vector is given. Then we have the magnitude of M as minus 1 squared plus 3 squared. Remember, the magnitude can never be negative. It will always be positive. There is no calculation for magnitude of a vector that will result in a negative answer. It will always be positive. Reason because we have the x coordinate, we have the x component squared, and then we have the y component also squared. So squaring any of the, or squaring the x and y components means that the answer will return as positive. So we have minus 1 squared as minus 1 times minus 1, and 3 squared as 3 times 3. So the result will always be positive. This gives us root 10 as our final answer. We can also decide to write that as decimal to the nearest the degree of accuracy we are asked to, if such arises in a question. Now we want to talk about the resultants of vectors. Remember, our focus is on column vectors. So how do we add and subtract column vectors? In the same way we have talked about the addition and subtraction, or the resultant of vectors when we looked at vector geometry. And vector geometry, remember, we're just using letters, small or lowercase letters, to represent the vectors, and we used those letters in the lowercase to find the resultants of vectors. Like you have here, we have the vector BE plus the vector ET to give us vector P plus Q as the resultant. The addition of vectors or the subtraction of vectors gives us a result that we will always refer to as the resultant. So if you have the vector P and the vector Q as given by the column vectors, we can add P and Q, and that will be the x component of P plus the x component of Q. That will be 2 plus 3, that's 5. Yet the y component of P plus the y component of Q, that will be 4 minus 1, and that's going to be 3. In the same way, we can also talk about the subtraction of column vectors. In the same way, we have added the first, in the first exercise that we did now, the same we will do for the subtraction. The x, that is 2 minus 3, that's minus 1. Then we have the 4 minus 1, that's going to give us a 4 plus 1, and that will be 5. We can also have other additions that involves the scalar multiplication of vectors, as we have earlier talked about scalar multiplication in our earlier lessons. So for example, we are finding the vector p plus 2q. We first have to make sure that this 2 multiplies every part of the vector q. What I mean is that it multiplies both the x and the y components of vector q. And then the resulting answer to that we add to vector p. So vector p is 2, 4, and then we have 2 times 3 minus 1. 3 minus 1 is the column vector for q. So if we do that multiplication, we're going to get 6 minus 2. Summing the two together will give us 2 plus 6, that's 8. And then we have 4 minus 2, that's going to give us 2. In like manner, we can have the vector q minus 2p calculated, and that will give us minus 1, 9. All of these vectors that we have found the resultants, p minus q, p plus 2q, and q minus 2p, all of them with the resultants given, we can represent all of them on the grid paper or on the Cartesian plane. Representing them all, we show the vector written as, we show the resultant of the vectors as a single movement against the movement in the p and the q directions, on the p and the 2q direction, the p and the minus 2p direction as shown. You can pause the video and take a look at this carefully. Now here are practice questions that we can take a look at on our own and work on following the examples that we have so treated. Next time when we meet in another lesson, we will be having to look at the final video on, we're looking at the final video on vectors, and in that case, we're going to be talking about the coordinates and vectors. We'll be talking about coordinates and vectors.